Hello, and welcome to the stream incision and geomorphology of the Yarlung River in the Himalayas. My name is Will Burrell. This is my poster. Go ahead and just dive right into it. Basically, I chose to do this research because the Yarlung River, as it lays right here, is right on top of the Yarlung Suture Zone, which is a currently active tectonic fault. So a river on top of a currently active fault seems kind of interesting versus like say the Mississippi River, which runs across the North American Craton, which geologically speaking hasn't seen any activity in a while, versus the Yarlung River, which sees, geologic activity very frequently. Um, so to do this research, I used GIS. That was the main platform that I used. NASA is really cool for a lot of reasons, but also because they have provided us with SRTM data. That's the Shuttle Radar Topography mission. Their goal with that project is basically to create very easily accessible, surface elevation models of the planet, which they're doing a very good job with. So I used that, created a DEM to do research with. First thing I did with that is I created these watersheds you're looking at right here. You can see them, they run right along the section of the Yarlung Suture Zone that I decided to do this research on. Next thing I did is I created a stream network using the stream network tool on ArcGIS Pro and a couple others, but that's the main cool one is the stream network tool. Basically what that does is it uses the Strawler method from geomorphology to define a stream network. Uh, a stream, like the highest stream in the drainage would be order 1. And then the lowest, like the main channel, would be a much higher number depending on how many streams exist between those two. So for my region, I had stream order from 1 to 11. And I found that 11 in this case was the exact match of the main channel of the Yarlung River, which is really cool because it's like this digital representation created using math that very closely lined up with how the Yarlung River actually sits today. And it has elevation data in it, which is very useful for the analysis. So then I cut this river that I had calculated up into sections based on which watershed it ran through to be able to look at how the geology of each watershed is affecting the behavior of the river. So get into the analysis of it here, I have it cut up into its sections. I calculated the sinuosity and the stream length gradient index of each section. And given the results of these calculations, there were two main and kind of cool conclusions I was able to make. First of all, the sinuosity is very low. It's around 0.8, which is incredibly low for a river and would classify it as straight sinuous. A river having sinuosity as straight as that means that it's incising. This river is barely depositing any sediment if it's depositing any at all. So it's rare to see a river that's that straight. So something is likely forcing this river to be so straight. The next big conclusion I was able to make based on the stream length gradient index, as well as the geology that the river is going through, is in a harder rock like granite, you would expect the river to be less steep. You'd expect a shallower gradient because it's harder for the river to incise in that granite. In a softer rock like sandstone and shale, which is basically everything south of the tectonic fault, you'd expect the river to be a little bit steeper because it's easier for it to incise through those softer layers. And I didn't see any such pattern. Basically, this river isn't reacting to the rocks as it should, which I think makes it safe to say that there's a larger process, likely tectonics, that is affecting the way that this river looks. Thanks for listening. Hope everyone has a great day.